and efficiency. This is an ongoing topic that is remain important for our customers, for our end users, for our across many applications. And I appreciate the opportunity to be able to share something that I think remains important for all these combustion processes. Just okay. All right. So in today's presentation on optimizing combustion processes for safety and efficiency, we will provide an overview of optimizing combustion, how to think about it, some of the working knowledge around safety and efficiency that, especially from a flue gas analysis perspective, things to think about for optimizing combustion. We'll talk about driving trends that are driving decarbonization that are requiring the need for greater fuel efficiency for emission reduction today as opposed to tomorrow. So how do you reduce emissions today and reduce fuel today? We'll also talk about safety margin at the burner, how to really get the air-to-fuel ratio right, and then how to think about that when it comes to optimizing combustion. And we'll then talk about the safety efficiency challenge. There's a trade-off that takes place that as you reduce one thing, you also have to potentially increase another thing. So you have to keep in mind the parameters around reducing, increasing safety, but also increasing efficiency. So we'll talk about that safety efficiency challenge as well, followed by some additional challenges that arise from changing variable. So how do you think about that? How do you mitigate different fuels, different circumstances that could certainly impact the burner and how to handle that. And then finally, we'll talk about additional measurements, additional means to measure and increase safety during startup and during home operation. Now, as noted, feel free to ask questions in the chat throughout the meeting, and happy to answer questions along the way. Okay, so let's get started. So to start off, we're going to first talk about the trends in decarbonization. Today, there's a lot of movement towards green energy, towards clean energy, towards reducing emissions, and all of that is driving what we call decarbonization. Governments globally have evaluated their role in, as well as corporations have evaluated their role in climate control to reduce greenhouse emissions with a primary focus as well on carbon dioxide. And for a lot of combustion processes, carbon dioxide is a primary molecule that's generated, and so there are commitments to reduce these CO2 emissions, and energy efficiency is just one of those ways to think about reducing CO2 emissions. Now, one other thing to think about is that there are a number of industries that are going to continue to require combustion, even with all the trends taking place. Even with electrification, even with there's still going to be a need for high temperatures and high heats for certain industries. So some hard to decarbonize industries include steel and cement and chemicals. They're certainly looking through their own different pathways to decarbonization, but they're going to remain. They're going to continue to need combustion for power and for heat. Same with mobility vehicles, ships, air traffic, trucks, and certain petrochemical and hydrocarbon processing applications as well. And then really, as we look at it from a global perspective, from a large-scale decarbonization perspective, there are a lot of different options available for decarbonization. There's carbon capture, which is one way to physically remove CO2 emissions before or after the combustion process. There's electrification to generate heat in place of combustion, which still requires a fuel source, but it certainly is one way to reduce emissions while also generating heat for certain applications. Hydrogen fuels are certainly important to generate heat without carbon emissions, as hydrogen doesn't have any carbon atoms to form carbon dioxide. And then finally, energy efficiency provides just another mechanism on a large scale to drive emission reduction, to reduce fuel costs, to focus on what we can do right now, those low-hanging fruits to optimize a combustion process right now. So ultimately, combustion processes will remain important in our future, and the measures that we take today for decarbonization will matter as we move towards a cleaner tomorrow. So with that, I just wanted to provide just a a very brief overview of combustion, just to level set some of how we think about combustion and combustion efficiency. So in any case, combustion will always start with a fire triangle. You need oxygen or some oxidant to drive the reaction. You need some oxidant or oxygen in this case. I need some type of fuel to receive those electrons, in this case fuel or methane or natural gas or any of those types of fuels. And you need some type of heat or spark to get the reaction going. So at a bare minimum, at a high level, combustion is really built on the foundation of the fire triangle, and you're going to need these elements of fuel, air, and heat to drive the reaction. Now, in a perfect world, all of the fuel and excess air would come together to form, will completely react to form carbon dioxide and water. And that'd be in a perfect world. In reality, though, we need an excess of air. We need just a little bit more air than fuel at the burner for safe operation. And as a result, we get more, we generate CO2, we generate water, but we also generate an excess of oxygen on the outlet. So the excess of air at the beginning generates an excess of oxygen on the outlet. And even if you look a little bit deeper into some of the process, you really form some amount of combustibles first. So before you go from fuel, and in this case as methane, to carbon dioxide, you actually first oxidize to generate carbon monoxide and hydrogen, and then with any remaining available oxygen, then the reaction continues to produce CO2 and water and some excess of oxygen. So in practice, we typically see part per million levels of hydrogen and part per million levels of carbon monoxide, with some amount of excess oxygen in the flue gas, in addition to the generated carbon dioxide and water formed. So this is a typical combustion application, and this is typically what we see in the flue gas. However, without enough air, we are confronted with unsafe conditions. If you have an excess of fuel, that potentially could lead to a hazardous condition where you generate percent levels of hydrogen and percent levels of carbon monoxide, because you don't fully get all of the oxygen, you don't fully get all of the energy out of the fuel. And as a result, it's less efficient and also creates a very unsafe condition for users. So we want to prevent an unsafe condition, and we want to make sure that there's enough air at the burner, so that there's enough excess oxygen in the flue gas, so that there's enough a safe operation of the burner. So that's why it's important to have an excess of air at the burner to generate an excess of oxygen in the flue gas. And really, together, we can use the feedback from the flue gas to inform the air-to-fuel ratio at the burner. So just as the burner produces the flue gas, we can also use the flue gas to inform how do we adjust the burner to meet the proper air-to-fuel ratio and to ensure that we have not only a safe operation, but also an efficient operation. So that's just a brief overview of combustion and just how to think about some amount of excess of air at the burner and how we generate some amount of excess of oxygen, as we also form some amount of part per million levels of hydrogen and carbon monoxide that we call combustibles. Now, when it comes to setting the safety margin at the burner, this is very important from an oxygen standpoint. So if we know that we're going to have, say, 3% excess oxygen in the flue gas, we should estimate that we have about 20% excess air at the burner. And that 20% excess air at the burner is important because that's a safety margin of 20% extra air. There's 20% extra air at the burner to ensure that everything's fully oxidized. And as a result, we have in this case, roughly 3% excess oxygen. So in the case of 3% excess oxygen in the flue gas, we should expect that to be roughly 20% excess air at the burner. So there is a direct correlation, and these are calculations I've made, and they're pretty stable across different fuels. So 3% for any 3% excess oxygen for any flue gas is generally going to be about 20%. When it comes to, say, even 2% excess oxygen in the flue gas, we should expect that to be around 12% excess air at the burner. So there's certainly this window of operation that we typically see for natural gas for excess oxygen between 2 and 3% for fired heaters, for boilers, for thermal oxidizers, and so on. And that 2 to 3% excess oxygen directly correlates to 12 to 11% to 20% excess air at the burner. So there's a direct correlation there that we see. And that's important because there is an extra amount of air at the burner so that you have safe combustion, and also that if you have some hiccups or some different fluctuations in your fuel, you have some safety margin to preempt and prepare for any variations in the fuel or in the operational conditions. So that's for natural gas. And if I were to preview it for hydrogen, it's very similar. So hydrogen, at 3%, 3.2%, it's roughly 22%. At 2%, it's roughly 12%. So it's still very much correlated, very consistent across fuels. And I've also tested this for different hydrocarbons as well, very steady around this 12 to 20% range. So when we look at this in practice, it's important to have this excess oxygen measurement so that we can provide that feedback to the burner. In the case with traditional fired heaters, the analyzer transmitter making that measurement of excess oxygen provides that feedback to the excess oxygen trim that supports the burner. That feedback is important so that it can adjust the amount of air that goes into the fired heater, and it provides us a measurement, a secondary visibility point to ensure that you have sufficient air to fuel, a sufficient air to fuel ratio at the burner. And so that's the case with traditional fired heaters. And then if you look at also with thermal oxidizers, it's very similar where the thermal oxidizer, as the flue gas, as the products of combustion are released, that excess air at the burner, that excess air at the stack drives the secondary air valve that introduces additional air or restricts additional air to the fire chamber. So again, you have this excess oxygen measurement providing that secondary air control point, and also that means of monitoring for safe air to fuel ratio at the burner. So really when it comes down to it, how do you know you have a safe amount of air at the burner? Measure excess oxygen. And so in the flue gas measurements that we mentioned, that's why it's important to have excess of air for normal operation, and that's also why it's important to have an excess of oxygen and to measure it in the flue gas. Now, how do you identify that optimal efficiency set point? How do you find what's most efficient? So for so before we can even start with optimization, let's talk first about the implications of excess oxygen. So say 2% excess oxygen is the typical operating set point. That set point represents some amount of NOx emissions. And at higher set points, there's a higher amount of NOx emissions, a higher amount of CO2. And the reason for that is because of higher fuel consumption. As you have more and more excess oxygen, you also generate more and more carbon dioxide and more NOx, and even higher fuel consumption. If you go even further, you have even a much higher CO2 and NOx emissions. So this correlation of excess air and excess oxygen also represents an increasing amount of carbon dioxide emissions, an increasing amount of NOx emissions, and an increasing amount of fuel that you're using at the burner. Now, if you compare that to a combustible measurement, as we mentioned, that incomplete combustion between carbon monoxide, of carbon monoxide and hydrogen, before you fully oxidize the fuel, the measurement is actually comparatively different. As you look at combustibles, as you increase excess oxygen, your combustibles decrease significantly because you have more air at the burner, you have more air to mix with the fuel, and that can more fully consume all of the fuel at the burner. So as excess oxygen increases, you have less and less combustibles. Now, the challenge, the safety efficiency challenge, is that as you decrease your excess oxygen, you also generate more and more combustibles. And those combustibles get to a point what we call combustibles breakthrough. And at this point of combustible breakthrough, you not only go from a linear amount of combustibles to a exponential increase in combustibles. So it poses a unsafe condition for both the operators, for the equipment, but also for the surroundings. So it's important to be mindful of how close you are getting to combustibles breakthrough, because it's not getting at 0% excess oxygen that's the issue. It's actually getting before that. Now, again, this is for illustrative purposes, but before you get to stoichiometric conditions, before you get to perfect air-to-fuel mixing, you actually see this before that. So how do we monitor for that? And it's important to have a combustible measurement to monitor for that. So as I showed you before, we have the oxygen operating set point of about 2%. That might be typical for a certain application. If we decrease to approximately 1% in this case, we avoid combustible breakthrough, but also reduce the generation of unnecessary NOx, fuel consumption, and carbon dioxide emissions. So as the excess oxygen measurement provides a set point by itself, combustibles provide an opportunity. It provides a secondary measurement for efficiency. So it allows you to reduce your emissions by lowering your excess oxygen and also by lowering your fuel consumption. And as a result, you've also avoid the unsafe conditions by being able to monitor for combustibles breakthrough and in conditions that are this astronomical increase in combustibles. Now, this is just an overview of the safety efficiency challenge and really making sure that you have enough margin at the safety margin at the burner for enough excess air at the burner, but also making sure you don't have too much excess air at the burner. Now, the one thing I want to point out is that this graph really depends on the fuels that you're using. So the target amount of combustibles really depend on the fuel. And in this specific diagram, you can see that natural gas, that might be between, that might be around or lower than 1% excess oxygen. But as you get as you start to use oil as a fuel, you might have to have a slightly higher window for optimized combustion versus coal. You need an even higher window of operation for combustibles for proper monitoring of combustibles and combustible breakthrough. So it really depends on the type of fuel, and not just the type of fuel, but also depends on other things such as the variable mixing, variations in the fuel. If you go from hydrogen to methane, you would need more air to consume the same amount of. You would need more air to consume the same amount of methane than the same heat release of hydrogen. So you need to balance it out depending on the fuel. So if you have variation to fuel, you need more safety margin. You need more of a window for accepting those fluctuations. So identifying the ideal excess oxygen level really depends on the burner type, the humidity, the fouling of the burner, the mechanical wear and tear. So there's really no fixed value for all cases. And as a result, we recommend measuring combustibles for that very reason, so that you have visibility on when you're getting close to combustible breakthrough, and if you were to have variations in fuel, that you have enough air at the burner to handle that. Now, one other thing I wanted to mention, I mentioned NOx emissions a couple times. NOx is generated from those hot spots within the flame. When you have poor mixing, you have a disproportionate amount of heat generated in a very small spot, and that disproportionate amount of heat exceeds high temperatures so high that they break down the nitrogen in the air to form to form NOx emissions. And these NOx emissions are very sensitive to the amount of air at the burner. So by monitoring your exhaust, you can also reduce your NOx emissions. And if I go further with that, this plot kind of shows you just a comparison of how these two things work together. So as I mentioned, that there's a correlation with as you get lower and lower exhaust, you have higher and higher combustible level. Well, it's actually just the opposite for NOx. NOx, as you reduce your excess oxygen, you have less oxygen available at the flame, and you have less potential to generate, less potential for the oxygen to come in contact with the air at high temperature to produce NOx. So there's very much a direct correlation between excess oxygen and NOx, and being able to reduce NOx emissions by ultimately finding that optimal set point for your process. Okay, so talking about NOx, talking about ppm levels of hydrogen and carbon monoxide, that's why we recommend having a combustible measurement to really provide that additional set point for visibility for combustible breakthrough and for optimization. And now next, let's talk a little bit about increasing safety during startup and process upset. So one thing that is important to think about as well during startup is just how do you, and also during normal operation, is how do you know if you have a burner that's leaking, or how do you know if you have a loss of flame, or in some cases, depending on the type of fluid that you have in your tubes, how do you know if you have a tube leak or some sort? So by having a hydrocarbon detector, it allows you to monitor for these high levels of fuel in the firebox where they shouldn't be. So monitoring for loss of flame, after you lose a flame, you start to see a cold zone around where the burner once was, and you start to see these pockets of unburnt fuel because they're not at a hot enough temperature to react to oxidize to create carbon monoxide, to create combustibles. So by having additional visibility for hydrocarbons in the firebox, you can prepare for those types of unsafe conditions. And these are things that we've seen during normal operation, again because of loss of fuel, and also because of loss of flame or leaking fuel at the burner or degraded burner tip, as well as during startup where say there wasn't enough purges. You could at least monitor for that and alert the operator that you have high methane, high fuel in the firebox before the next light off. And so, in the case of a fired heater with multiple burners, multiple detectors would provide that ability to look across zones as well. So it's also important to think about, well, how big is your firebox so that you can monitor for the different various zones that you have in front of you. So again, important to think about a methane hydrocarbon detector to alert for loss of flame, to alert for high fuel rich conditions. So when it comes down to it, really measuring the excess oxygen, measuring combustibles, measuring fuel provide the first three critical measurements for flue gas analysis and for safe and efficient combustion. And if I were to add on just a fourth critical measurement, I'd also not only add the oxygen that we talked about with the oxygen, the fuel, and the heat that we mentioned about the fire triangle, not just the combustible that we talked about with malfunctioning burners, but also I'd add sample flow to ensure that you have an accurate representation of the process especially for a burner that might be extractive or have a potential to pull in particulate. It's important to notice that you have an accurate representation of the sample and that it's pulled in accurately. So,
Tim, there's a question in chat.
Sure. So, question I see: what would be the change of control logic if carbon monoxide equivalent? I'll get to that question in the end. This is a good question. Let me get to that. I'm just about done now. I'll get to that in just a moment. Just reiterating the fourth critical measurement, not just being excess oxygen, combustibles, methane, but also sample flow. As far as takeaways, some things I really want to just keep in mind. Again, excess oxygen provides that operational set point to ensure that you have enough excess air at the burner for safe combustion. It provides that air-to-fuel ratio correlation, like I mentioned. Very important from that standpoint. It's required for safe monitoring of the fuel and that air-to-fuel correlation. As far as combustibles, for efficiency and for safety, again, combustibles provides that part per million level monitoring for hydrogen and carbon monoxide. It provides safety monitoring for combustibles breakthrough, and it provides an additional secondary measurement for optimization of the air-to-fuel ratio at the burner. And then finally, for measurement of hydrocarbons, which includes percent levels of hydrogen as well, as long as you calibrate with hydrogen. But again, that allows you to monitor for fuel leaks, for safe light off, and for any potential tube leaks, as long as it's not too big of a hydrocarbon, but also just monitoring of tube leaks as well. So just as a quick takeaway slide. Now let me pass it over to questions, and thanks, Carla, for pointing out that we have a question. I see that we have, so the question is, what would be the change at the control logic level if carbon monoxide equivalents, or COE, mediation were incorporated? Most clients operate with excess oxygen to improve combustibles would have to be measured. So let me know so let me answer this question, and if you have a follow-up, I'm happy to answer further. So the change in control logic. So one of the things that API 556 recommends is having certain interlocks for monitoring for combustibles. They certainly have the low oxygen override, but they also have, or the low oxygen interlock, excuse me. But there are two additional interlocks that they recommend per API 556. One is the high combustible interlock, and then also which is around 500 parts per million. That's just roughly what they've noticed as a good rule of thumb for fired heaters is around 500 ppm, just to have a first pass alert for approaching combustible breakthrough. So that's around 500 ppm, and that's again the first alert, the first high combustibles interlock. The second one is the high combustibles shutdown, and that's when it exceeds a certain value. Now, for fired heaters and refineries, we've seen that value to be approximately 1,500 parts per million of combustibles. But that's really where there's, if not a shutdown, there is at least a much stronger investigation on what's going on to ensure that the analyzers, to ensure that the firebox is diagnosed correctly. Good question. I hope that answers your question. But yeah, that's what I would say as far as an addition. I would think from a control logic standpoint, you at least need the visibility to monitor for high combustibles and high combustibles, very high combustibles. Those two additional interlocks, and then at least to provide those alerts to the operator. As far as shutdown, that's more of a plant-related decision, but it's important to at least have that visibility for measurement. Now I see that the second question is, does hydrocarbon measurement apply for all types of combustibles? For coal, for biomass, for bunker? So that's a great question as well. Thanks for asking. So the combustible measurement is specifically designed for measuring that incomplete combustion in the form of carbon monoxide and hydrogen, and really anything that's able to react within that reactive zone of between carbon monoxide and hydrogen. So as far as any type of combustible, it really it's not so much it depends. It's like as long as there's going to be incomplete combustion of carbon monoxide and hydrogen. So in most cases, yes, because let me answer this question a little bit more clearly. The combustible measurement will measure carbon monoxide and hydrogen and anything in that window. The hydrocarbons measurement, is slightly different and a little bit more particular. So the hydrocarbons measurement can measure light hydrocarbons like methane, like ethane, like propane, in some cases butane. As it gets bigger and bigger as it gets more complicated to things like coal or like biomass or bunker, a hydrocarbons detector would not measure those particulates like coal, or they would not measure those particulates like biomass. Those are all particulate heavy, and so the hydrocarbon detector is more designed for those light hydrocarbon fuels that we see at the burner, or it's like as a supplement. For things like coal, it'd be more important to have like a combustible measurement. For things like biomass, again, combustible measurement. But if you light off with hydrocarbon, then I'd recommend monitoring for hydrocarbons. I hope that answers your question. Good question there related to the hydrocarbon measurement. Okay, as far as the next question, so thanks for sending the next question in the chat. So the next question I see is, would there be benefits of measuring fuel gas composition upstream of combustion? Specifically like hydrocarbon blended, the percent of hydrogen blended into the fuel. Yes, the measuring the composition in the fuel is very important from the standpoint of being able to be proactive to fuel changes. When you fire at hydrogen as a fuel by itself, it needs X amount of it needs so much air. When you go from for the same heat release, so when you go from hydrogen to methane, though, methane for the same heat release needs 20% more air compared to hydrogen. So, so at a minimum, it's important to be mindful of when are you fluctuating between fuels. Now, I understand that some fuel headers vary in composition, so in some cases it's not easy to have that information. But if it's possible to measure the amount of hydrogen or measure the amount of variation in your fuel composition, specifically related to the heat need or the oxygen need, that's important because that oxygen demand will preempt the oxygen analyzer, and then you could add more oxygen more air at the burner. So I think it's certainly that's one way to improve the safety and also to prepare for variations in fuel. So yes, I think it is certainly important to monitor for fuel gas composition upstream if possible. And if it's not possible, I will recommend a higher excess air at the burner, higher level of excess oxygen in the flue gas, so that you can be prepared for those fluctuations, especially if it's like hydrogen to oxygen, where especially where it's from hydrogen to methane, where methane needs 20% more air compared to hydrogen. Good question there. All right, I see one more question in the chat. Feel free to add any other questions if you think of any. So another question I see is most customers have a SEMS analyzer system and integrate the signal for the combustion control loop. The system that most of the time is not reliable for combustion control. What is recommended? So I appreciate SEMS measurements. They're absolutely important, especially from the stack perspective. Before we release emissions, it's really important to have visibility on that for emission monitoring and for regulatory standpoint and compliance. When it comes to monitoring the combustion firebox real time, that's where I think about having a flue gas analyzer that's like right outside the radiant section. So if it's a fire heater, right outside the radiant section. If it's a thermal oxidizer, it's towards the it's after the reaction time is completed, after the proper residence time is completed within the chamber. If it's a boiler, it's after the radiant section. The importance of this is that you get a faster response with a flue gas analyzer that's designed for combustion control. And that allows you to have a faster response to prepare for unsafe conditions. So a faster response in the case of having combustibles breakthrough, in the case of having variations in fuel. For certain applications, you can get an oxygen measurement in less than 15 seconds, an oxygen measurement in less than 11 seconds, combustion measurement in less than 30 seconds. Like, those are important because you'll have more time to respond to an unsafe condition compared to a SEM system that's probably further down the process, could be downstream of waste heat boiler, could be downstream of other types of equipment that would not provide the most real-time measurement for monitoring the combustion and for supporting the combustion control process. So that's a great question. I certainly see that SEM systems have their place, but also from a combustion control standpoint, it really helps to have something closer to the firebox, something that's able to measure and respond quickly to those variations in fuel in the firebox itself. Okay, great question. So I see another question in the chat, and feel free to keep asking. This presentation's for you. So the next question is do you have a general reference for where you would recommend to install the analyzer? Yes, I sort of given some answer to that earlier. The American Petroleum Institute, the 556 recommended practice, second edition, they recommend that for fired heaters, that the flue gas analyzer be located right outside the radiant section. You need enough time for the combustion to take place. You need time to be outside the burner flame and the burner envelope, in the flame envelope. You also want to make sure that you have sufficient time for the reaction to take place, but you don't want to be you don't want to be in the flame where the reaction is taking place, and there's going to be a lot of variability. So it's important to have. So what API 556 recommends is that you put it right on the radiant section, right at the end of the radiant section, so right before the convection section. And that's important because it reduces the potential for tramp air or ingress air from the outside to come and bias the oxygen measurement. So there's less risk for ingress air. There's also more opportunity for more opportunity to get a measurement that's reflective of the firebox in the process than downstream. So that's what they recommend. Again, for a thermal oxidizer, I'd recommend it after the residence time is taking place. So in some cases, it's 1 second residence time instead of in some cases 1.5 or half a second residence time. Wherever that mark is, typically there's going to be a thermocouple there. There's going to probably already be an oxygen measurement there for a thermal oxidizer based off its design to make sure there's enough excess oxygen to consume the fuel. Also, for a boiler, again, I'd also reiterate that it's very important to have it after the radiant section, but not too far after the radiant section. In some cases, for a big boiler or for like a industrial boiler, it's important to have it maybe before or right after the convective section, depending on how many tubes there are and depending on the layout and where it is for sample point. But those are some of the recommendations I'd recommend. I'd really focus on the right after the radiant section. And I'd also be mindful of installation so that there's no tubes in the way or that there's no beams or debris or dust in the way that could interfere with the measurement as well. So that's also something I'd be cautious as well, that not only is it in a spot after the radiant section, but also that it's not interfering with the tube and there's a dead zone where there's not able to make a measurement. That's something to think about as well. Okay. I see we have another question too. What happens when you have a multiple burner boiler? Is it recommended that more than one analyzer? That's a great question. I will defer to the API 556 recommendation. The short answer is yes, but the long answer is it really depends on how big the firebox is. For a fired heater that may have 8 to 12 or more burners, API 556 recommends that you have at least one analyzer every 30 feet or every 10 meters. So in the case of a multi-burner boiler, I'd be mindful of how far apart are all of those burners, and is it less than 30 feet? In which case, maybe one analyzer is useful, or is it getting close to 30 feet where you might need to have two just to make sure you have enough zone visibility of each zone within the boiler? Great question there. So the short answer is yes. The long answer is for a fired heater, it'd be one analyzer every 10 meters or every 30 feet. For a boiler, I'd probably recommend something similar. If it's becoming too big of a boiler and has many burners, I'd be mindful of how big is it and does it make sense to have one analyzer for a flue gas measurement, or do you need to space out maybe one every 10 meters or so? All right, great question. A lot of good questions. I see another question on any recommended product to measure oxygen combustibles for high particulate matter for high temperatures. Yes, we have a specific high particulate analyzer that we released in May, the next generation version of high particulate analyzer, the WG5HP. That's been used tried and true. Its predecessor, the WG-HP2C, was used tried and true in very heavy particulate applications in cement and lime and pulp and paper and industrial waste. And we continue to recommend that particular product for high particulate applications. We have other options too if there's a light amount of particulate, but if it's very high and very high temperature, I'd be the first to recommend the WG5HP for that application. Okay, great questions. All right, well, feel free to type in any other questions in the chat as we kind of wrap up. Again, my name is Tim Town, the Combustion Product Manager here at AMETEK Process Instruments. Feel free to email me via my email or call me on my work cell phone at this number. With that, I really appreciate your time and attention. I see that there's one more question. I'm happy to answer that question. I do appreciate your time and your attention in this webinar today. I'm going to answer the next question, and then we can conclude. So the latest question that I see here in the chat is that, what's the difference between a high particulate HP analyzer and a blowback analyzer? The difference is actually all the practical things that you could think about. A blowback analyzer is designed well for dusty applications that don't have dusty particulate, not sticky particulate. That's one important thing. So something that does not stick to the filter, but rather it blows off. It blowbacks off the filter. The blowback also is good for generally less than 30 grams per meter cubed of particulate. So there's a window. If you have too much particulate for a blowback analyzer, it can perform, but it provides less and less blowback over time as the filter starts to plug, and also as the filter starts to accumulate more and more particulate on it, and also as there's more and more blowback cycles required. So a lot more instrument air needed for a blowback analyzer. So that's something I think about. I think about the type of particulate, I think about the pressures, I think about the frequency of blowback cycles. I also think about the time to actually, there's going to be a point where you have to clean off the filter from a blowback. So just being ready for that as well. For a high particulate analyzer, like the WG-HP2C or like the WG5HP, in both of those cases, it's high particulate because it's a very specific different design. It doesn't use an aspirator to pull in a sample. Rather, it uses convection and diffusion and the pitot tube effect to pull in a sample. And those effects are able to measure excess oxygen, are able to measure combustibles, are able to measure methane at a slightly slower rate, but also in a way that can bring in a measurement and not plug the filter, not plug the inside of the analyzer as fast. So it can handle much higher levels of particulate because it's a slower related motive force, if you will. Okay. All right, with that, good questions. Any other questions? I can certainly hang on, but I definitely thank you for your time and for your attention. Tune in for the next webinar that we have in December as well, coming up. So look for that. And with that, I thank you for your time. I'll be on for any other questions, but thank you for attending today.